All right, thanks, Andy. And it's really exciting to be here tonight. Thanks for coming out in the evening. And I've got a presentation prepared here for you, and I will include what I think are some highlights of the mission so far. And I hope you agree. And I don't know how these work, but you can, if I can see you, you can interrupt with questions. But if not, save your question for the end too. I hope there's time. I didn't want to make it too long, so we'd have time for some questions too. So, well, let's get started. So, well, actually, I should say before we get started that my role in the mission, I think Andy mentioned too. I'm the curation lead. So the very end of this mission culminates with samples coming back to Houston. And so I'll talk a little bit about that. My presentation is a little bit biased towards samples and curation. So, and that's why. So different team members could come up and give a talk on this topic, and they'd all have a slightly different bias, but that'll be mine for tonight. Let's see here. So I wanted to just get started right off the bat with a couple of images to whet your appetite. So these are a couple of images that were taken from of the surface of Bennu probably a couple months ago. We've had these for a while, but to me and to all of us on the team, I think we were really surprised at the how spectacular these are. To me, they look like scree slopes out in Montana, or they look like, which are the slopes of loose boulders that come off of steep mountains. Whoops, it's not exactly what they are. It's just a rocky surface though. And some of these are quite large. This one is probably 20 to 30 meters in size, and it's really dark too, which I'll talk about a little bit later. But you can see how large. There's some back here that are 5 meters, tons of 1 meter boulders. And so this is a surface that a lot of us were expecting to be made of finer grained material and be smoother and easier to pick a sampling site. So we'll talk about that a little bit. Anyway, I just wanted to show those right away because they're so cool. This was okay. So this was taken with one of the cameras on the spacecraft that has I think it's an 8 centimeter. Let's see. It's a small telescope. I shouldn't give dimensions. I'm not sure of, but it's a small telescope, and it has a range of capabilities. I think this was probably a mile or two away. Yeah. So yeah, still pretty amazing. Okay. So anyway, we'll start out with a little background on asteroids, and I couldn't help but put this slide together because most of us, when you hear the word asteroid, you might think of the video game or one of the movies like Armageddon, or even like a Gary Larson cartoon might jump in your mind with like this one. Gary Larson always drew the greatest asteroids. And then I remember this postcard when I was a kid. Somebody sent this to me, not this exact one, but it's it's like a cartoonish asteroid belt. So really, what do we really know about asteroids? more than that. So the asteroids were the two largest asteroids, Vesta and Ceres, were discovered in the early 1800s. Ceres was discovered by Giuseppe Piazzi, who was an Italian monk, with this instrument right here. I think he was in Palermo. And Vesta was discovered by Olbers in 1807, so 6 years later. So anyway, these asteroids go way back, and these are some of the first to be discovered. We've learned a heck of a lot since then. So now we know there's this gigantic asteroid belt that exists between the orbits of Mars and Jupiter, and it's this fuzzy green cloud here. And then we also know that there are Trojan asteroids that are sort of in a gravitational stability point on each side of Jupiter's orbit. So they're you might hear about Trojan asteroids every once in a while. That's where these reside, at the L4 and L5 points. So there have been many systematic searches and observations of asteroids in the past really almost 200 years. And we know quite a bit about them now, including orbits, their masses, brightness, or albedo is another word you hear for brightness, or reflect intensity of reflection, and then also composition. I'll talk about in a later slide. But one of the features of the asteroid, the main belt asteroids, are these gaps. These what they call the Kirkwood gaps here. These are caused by gravitational or orbital resonances between the asteroid, an asteroid, and Jupiter. And so there are these different ratios here. I'll step away. So, orbits the asteroid makes, or a number of times it rotates, orbits the sun and catches up to Jupiter. So that every time it passes Jupiter, it'll push material slightly gravitationally, and that causes these gaps to form in the belt. And so that's one way that the belt has structure, and asteroids get distributed this way. But another way is in their orbital characteristics. They get these they acquire these two physical parameters we call inclination, which is illustrated here, which is the tilt of the orbit plane, which is in yellow there, relative to the equatorial or to a reference point. So the inclination of asteroid orbits is plotted here, and this is used to delineate the different families. And you can see there are many families here, some of them with inclinations approaching 20 degrees. And then the other variable is eccentricity, which is really a measure of the non-circularity of the orbit. So, really eccentric orbit is shown here as the ellipse, and then a very low eccentricity is the one in the center here, and that's plotted on the x-axis. So these two parameters allow quite a range of value of distinction and structure to be identified in the asteroid belt. So we've learned a lot of these physical kinds of characteristics. And then the imaging has changed quite a bit too. So I showed this telescopic image shown here on the left from this is the kind of images they took in the 1800s and into the 1900s. But along came the Hubble Space Telescope in the 90s, and this is an image of Vesta that was taken in 2007. So a little bit far into Hubble's lifespan, but it was an amazing image at the time, but it's still a bit fuzzy compared to what we have available now from other missions, which I'll show you. But Galileo probe to Jupiter took this picture of Ida, 243 Ida, in the late 90s and early, I think 2001. The NEAR spacecraft took this image of 433 Eros, and then the Dawn spacecraft more recently, just a couple years ago, took this image of Ceres, which is really detailed. These are large bodies. All of these are large bodies, so you can kind of get a sense for how the resolution of the imaging has improved over the years. This is just a timeline at the bottom that shows the number of missions and their duration since the 80s that we've had that have helped us understand asteroids a little better. And then you can include a few more missions. We've had maybe a total of 9 providing new information about asteroids. I like this slide because it shows the 2 larger asteroids here on the bottom, Ceres and Vesta, and then they're little spots you can barely see to their right, which are these asteroids enlarged over here. So these then they scale down, and just to put things into perspective, Bennu is the second one from the right here. This little point. And it's so small, it's circled. So what you see is the circle. So anyway, that gives you a sense for the scale, I think. So what else do we know? So the interesting thing to me as a meteorite curator is that asteroids have been connected to meteorites in our meteorite collections, and there's some that are very specific. This is one example. So one technique that astronomers use is to look at infrared spectral reflectance features. And if you look at, you plot up the intensity versus wavelength for Vesta, the curve looks like this. It's a kind of a squiggly S-shaped curve, S on its side. And then it's in asteroid terminology, we call this a V-type. It's a V-type spectrum. There are these others I'll talk about in a minute. But the distinct features in the V spectrum actually match up with a kind of meteorite we call eucrite. And there's a picture of one here in the lower left. This is a eucrite from our collection, brecciated. You can see the clasts that are that incorporated into this breccia, a combination of fine-grained material and these coarser clasts that are lithified together into the rock we call a breccia. And then here's an image of Vesta taken by the Dawn spacecraft showing the great detail. Anyway, this connection was first proposed in the 70s by McCord and was strengthened by the Dawn mission imaging and measurements that were made in 2011 to 2012 kind of time frame. So this is one example. We have actually about 1,000 samples that we think may have come from Vesta in our collections worldwide. So it's that's a really valuable connection to make. On the other hand, there is another large class of asteroids we call S-types. Those are shown here, and they also are a squiggly line in their plot of wavelength versus intensity. And in this case, the distinctive features you can see match pretty well with, so what's shown here is asteroid Itokawa, which was the target of the Hayabusa mission back in 2010, 2011 timeframe again. The squiggly line here, the top one, matches pretty well with what we call an LL chondrite shown here. And so we're not saying that all LL chondrites came from Itokawa, but just the opposite. Itokawa is made of material like LL chondrites. So this is a connection that's been able to be forged as well. But this is a smaller body. So this is half a kilometer long. And one thing you'll notice here, see all the smooth spots on Itokawa, even out in the central part? This is sort of what we were expecting for Bennu. And it's quite different, as you'll see. So anyway, let's see. There have been detailed surveys, and while we're talking about composition, one thing I wanted to really, point I wanted to make clearly to you is that if you look, again, this is the asteroid belt distribution. It's a plot of the semi-major axis, which is basically the distance from the sun in astronomical units, and then as a plot against mass. So this is the mass distribution. There was a study that came out about 5 years ago that showed the inner part of the asteroid belt is comprised mainly of these S-types, whereas the inner and the outer, especially the outer belt, is comprised mostly of C-types. So the C-types turn out to be volatile rich and probably carbon rich, carbonaceous. And let's say it's about 50 to 60%. If you compare that to our meteorite collections, there's only 5% in the meteorite collections. So we're getting a delivery bias of material to the Earth. We're getting a lot less C-type material delivered to the Earth as meteorites. So that's kind of a interesting fundamental takeaway point, I think. But it turns out, as you'll see in a few minutes, that's one of the reasons we're going to Bennu to try to fill in that gap. So I'll mention really quick, there's an spacecraft called NEOWISE, which is undertaking a survey of asteroids, and it's been increasing the number of asteroids documented by thousands and thousands. I forget how many they're up to now, maybe over 200,000 asteroids identified of all mass ranges, and very valuable kind of survey to do. Anyway, I don't think there's any NEOWISE data in this plot, but I wanted to show it in this context for you. You may hear about it in the news occasionally. So what have we learned from asteroids? Well, here are a couple of high points. I wanted to show you a little bit. I don't want to talk about all of this in a lot of detail, but we've learned that most of them are ancient, dating back to the beginning of the solar system. Some were hot enough to have melted completely. Some are unheated and did not melt, and then there's some in between. So they record a range of temperatures that existed in the early solar system. Their orbits have changed over time, and those are influenced by the orbital motion of the gas giant planets, mainly Jupiter, but also Saturn, Uranus, and Neptune. And then they also preserve asteroids, just their surface features, basic surface features, preserve a record of impacts in the inner solar system, which can help us understand orbital dynamics and impact processes in general. So these are some basic things we know, but what is it we don't know, or what are some outstanding questions? And so I've listed a few here, and these have actually helped to drive the OSIRIS-REx mission and give it some what motivated the mission. So one of them is the forces that drive the orbital change of asteroids. Why do the asteroids move around and on such a small scale but large scale over great lengths of time? This is poorly understood. What's their internal structure? That's also poorly understood. I'll show you in a minute. Did organic compounds found in asteroids contribute to life on Earth? This is currently debated. We don't know, but maybe. And can we make any other connections between asteroids and meteorites? This is a really good one too. Could be valuable for meteorite science. And then how different are pristine asteroid samples and meteorites? So meteorites, we know, are affected by weathering, by sitting on the surface of the Earth, and then heating. As they come through the atmosphere, they heat up, and their properties can change. So if we go collect sample directly from an asteroid, we get around all of this these secondary processes on the Earth. So for OSIRIS-REx, that's all background for OSIRIS-REx. So here are good reasons to go. No previous missions have visited or returned samples from a carbonaceous asteroid. All those images I showed you earlier were either S-type or V-type, no C-types. And I should mention that JAXA, the Japanese Aerospace Exploration Association, they have a Hayabusa 2 spacecraft right now sampling and imaging and characterizing a carbonaceous asteroid. So there are two of us doing this at the same time, which is also really exciting internationally for international science. So the special thing about OSIRIS-REx, to me, is that we'll get a sample. So we won't have to really speculate about what the mineralogy is, what its composition is, what's the age, what are the rock types, and what processes operated on the asteroid. We should be able to constrain all this because we'll be able to study these samples in our own labs on Earth. And also having the pristine, unaltered material will get around this uncertainty that's introduced by sitting on the Earth's surface by meteorite studies. Okay, so what is OSIRIS-REx? So that was a lengthy preamble, but I hope it helped bring everyone up to speed and get you excited about this mission. So, but then we're gonna ruin that with a horribly long acronym. So OSIRIS-REx is an acronym. It's the O is origins, the SI is spectral interpretation, the R I is resource identification, S is security, and then RX or Rex is the regolith explorer. So the spacecraft or the mission has all these features built into the mission plan, and the plan is to return at least 60 grams and maybe as much as 2 kilograms of material from the carbonaceous regolith from Bennu. So let's find out a little more. So the OSIRIS-REx mission was put together initially in 2007 as just OSIRIS, maybe even 2006, and they did not get selected for the Discovery program, NASA's Discovery program, and they kind of reorganized and hit the reset button. They added Rex to the name for Regolith Explorer and submitted to the New Frontiers program in 2009. They were invited to do a concept study report in December of 2009. That means they picked 3 or 4 of the proposals and said, okay, we like what you've done. Let's hear some more detail. And so they did, and then after that they were selected in May of 2011. So the point of all this is to let you realize how long the process is for these missions. So picked in 2011, you'll see later it didn't launch until 2016. There's a lot of work that goes into making this happen. But the PI of the mission was initially Mike Drake, and Mike passed away in late 2011, actually. And Dante Loretta, both of these guys at University of Arizona, took over as the PI. The other institutions involved are Goddard Space Flight Center doing the project management, and some of the one of the science instruments, the OSIRIS, the visible and infrared spectrometer. Lockheed Martin did the flight system, so the spacecraft and a lot of the components, the SRC and mission operations. And then other instrument institutions involved with the instruments are Arizona State University. They had the thermal emission spectrometer, and Canadian Space Agency provided the laser altimetry. Company called Kinetics did the navigation. And then here at the bottom, last but not least, sample curation here at JSE. So it's a big team. And these are, the science team is even larger, actually. I won't list all the science team members. But the target asteroid was selected. When it was selected, its name was 1999 RQ36. So the PIs decided we need a better name. And so they had a naming contest. And this guy here, Mike Puzio, I think this was a 2010 or 2011, he proposed the name Bennu, which is has a connection in mythology to Osiris, and Bennu is a heron. So the team liked that name and selected it and made him a happy guy. So, but Bennu was selected from nearly over 500,000 asteroids. Greater than 7,000 of these are near-Earth asteroids, which you need to have. And these numbers may be slightly out of date too, so they could be even higher. There are 192 of those with optimal orbits for sample return. 26 of those with a diameter greater than 200 meters. And then 5 of these, 26, were carbon-rich. And from those 5, they selected Bennu as the winner. So why is that? So you can see Bennu's orbit here is the blue circle, and you can see it's an Earth-crossing asteroid. So at certain times of the year, it's a year that's within Earth's orbit, and it crosses over between Earth and Mars for the other part. So why Bennu? Well, the team felt that it provides the most exciting science. It's the lowest albedo or lowest reflectivity of any known asteroid, 0.03. Actually, I'll show you later that they verified that with a boulder on the surface, but I just realized right at this second that they knew this already when they were selecting Bennu. It has a very low albedo. It's probably the lowest known. Yeah. Anyway, so that's spectral signature combined with the low albedo suggests a carbon-rich and volatile-rich body, which has never been visited before by spacecraft, which I mentioned. An important thing is that its size, its general shape, and rotation state were known from a lot of the observations that were made by these instruments. It was discovered by the Linear project, and there were data from the Spitzer telescope and the Arecibo radio telescope providing constraints as well on Bennu. This is a shape model. This was before I think even before launch, they put this together. Which is actually turns out to be fairly accurate. This crater, though, I don't know about that crater. That looks a little suspicious and sharp-edged. Well, we'll see. We'll see later. There's also abundant regolith. At least they thought there was, and we'll look at that too. And then the other thing is this particular asteroid has an orbit with a high uncertainty, and it's Given that, it has a fairly high probability of impacting the Earth in about 200 years. So, but again, it's got a really large uncertainty in the orbit. So that got the attention of NASA and Congress as well. So this is a good one to learn more about, just more about its orbital characteristics. So how large is it? It's about 500 meters, and I love this slide. Really hits the point home, a little bit larger than the Empire State Building and the Eiffel Tower. So let's talk a little bit about the spacecraft. So these are kind of hard to see, but this is a schematic diagram on the left, and then a photograph of the spacecraft as it was being built. There are a number of instruments on board. There's a visible infrared spectrometer. There's a thermal emission spectrometer. Both of these can tell you about either volatiles or mineral identification. There's a camera suite that has cameras that are designed for different parts of the mission. Right now they're using Polycam. They used MapCam on the way to Bennu, and they're going to use the SamCam when they're doing sampling in the upcoming months. There's also a Rexus X-ray imaging spectrometer. The TAGSAM is what we call this sampling head right here that's at the end of a sort of an elbow-shaped pogo stick, or a pogo stick with an elbow in it. I'll show you more about that in a minute. And then I don't have listed here OLA. OLA is the altimeter, which is, according to our colleagues, is providing incredible data on the topography of Bennu, and that was built by Canada. So the spacecraft was assembled and tested in Colorado by Lockheed Martin in the time frame of January 2015 to May 2016. And then it was flown to Kennedy Space Center for launch. So I put together some images that sort of show the flow of production here, starting with the very early. They started earliest on putting together this sampling head, which I'll show you more about in a minute, and in its clamshell cover. And once they had that connected and working, then they attached it to the spacecraft, the main spacecraft bus in their high bay. It went through some series of tests, acoustics tests, simulating the launch and other parts of the journey. The thermal vacuum chamber simulating the space environment, and then finally, when it passed, they shipped it from Denver to KSC in this big box and this C-130. These are the kinds of details I like to show, so I hope you like to see it too. Anyway, then once it gets to Florida, it goes into this Payload Hazardous Servicing Facility, is the name for this building. It's just a big clean room where they start assembling the last parts, and they get it into this payload cone here and start transporting it toward the launch pad, shown in the background there, and then they get it up on the lift. They lift it on they call this the Vertical Integration Facility, or the VIF, lift it up there and put it on top of the rocket, and here it is in place, finally, at the here, and then at the top, at the very top. And so September 8th, 2016, it was launched, and it was a great launch. I think it launched 100 milliseconds or something like that into the launch window. They were making a big deal about how they had a 3-week launch window, and they and then they launched in milliseconds. Anyway, it was great. That's the first launch I've ever seen. And anyway, so that was it's amazing to think it's almost 3 years ago already. So since then, the spacecraft has reached Bennu, and in fact, it reached Bennu and started the approach maneuver, I think, in November and December of 2018, and then began what they call asteroid operations. So they did a preliminary survey that lasted several months, and then they'll do sample collection, just to go through the schedule here real quick. Sample collection in July of next year. They'll have departure maneuver here in early or kind of spring of 2021, and initiating the return cruise. And then when it gets close to Earth, that SRC, this part right here, that will be released, and it'll fly down, zip down through the atmosphere and land in Utah. And we'll have a big team of people there waiting for it, for its arrival. So progress so far, and we'll come back a little bit to the mission, but progress so far. So a lot of things have happened. I won't talk about all of this, but here's a list of some interesting highlights. Well, of course, the instruments were tested on the trip to Bennu. That was a couple-year cruise. They encountered Bennu in 2018, December 2018, carried out preliminary surveys between March and May. From these kinds of measurements, or the survey data, they were able to determine the mass, shape, and density of Bennu, its rotation rate and acceleration. And they also found evidence for hydrated minerals on from imaging the surface. And I'll talk a little more about that. Particles are being ejected from Bennu. That's what this photo is here. So there are hundreds, sometimes dozens of little particles being ejected from the surface that they caught in some of their images. And so that was exciting, totally unexpected. A lot of the boulders are dark and they're perched. I'll show you what I mean by that, by perched. Cratering ages are estimated to be 100 million to a billion years in age, and we'll talk a little bit more about that too. And then finally, they generated a global map for selecting the sampling site. If you really want to get more into this, there were two special issues of Nature and Nature Astronomy, where there are, I think, a combined total of 6 or 7 papers about the mission from, I don't have the dates, but I think it was April or May, probably May. So anyway, if you want to follow up on any of this in more detail, I would recommend looking at these. They're interesting issues. So first of all, they determined the mass, shape, and density. So you remember that I showed a shape model maybe 10 minutes ago. Here's the updated, revised model. They're strikingly similar. They did a great job, I think. But it has a sort of a spinning top shape. There's some irregularities, but it's sort of symmetrically bulged at the equator. And so that was the shape is one thing they've been able to constrain pretty well. The mass determination was done by using radar and radio science. As the spacecraft approached Bennu, it could detect gravitational shift due to the gravity of Bennu, which is a tiny asteroid. But it was large enough to be detectable using the Deep Space Network. And from that, they could make a mass estimate. And so using the shape and the mass, they calculated a density for Bennu. I think, is it not? Oh, here. Yeah, here it is. Yeah, it's very low, 1.2 kilogram or grams per meter cubed. It's very low compared to meteorites, which are 2.5 to 2.7. So what this might be telling us is that Bennu, I put this little cartoon at the bottom. Bennu might have very high porosity, maybe 50%, that might be indicating that it's what scientists call a rubble pile. In other words, it doesn't have a shell structure like a lot of planets do, where you have a core, a mantle, and a crust. It may have started with material like that, but it's been brecciated and impacted and broken into pieces numerous times over its history, and now it's a sort of a pile of rubble. And there's porosity in this pile as well. So this is a sort of a rough working hypothesis. I'm sure more work will be done on constraining its interior structure as the detailed surveys go on. The spectroscopy has been exciting. When they first got there, they realized right away that Bennu, which is the black line at the top, has this infrared spectrum with a pronounced trough here around 2.7 microns, which is similar to the trough that we see in these carbonaceous chondrites that are full of the mineral serpentine, which is a phyllosilicate, which has water in its structure. So they immediately concluded, hey, we've got water on Bennu, which is exciting, but it's also the reason we chose Bennu. So it was a good confirmation. If you look at other wavelengths, there's a feature out here too that's associated with phyllosilicates, and we see that as well. And these are reported in one of those journals that I pointed out a few minutes ago. Okay, so anyway, spectroscopy was exciting. I mentioned the dark boulders. Here's, I think, the darkest one, which has a reflectance of 3%, I think. Yes, 3.3% albedo, which is very low. And like I said a few minutes ago, they had predicted it would be low even before launch, which I had forgotten. So anyway, this was neat to see it show up here in a big boulder like this. With the other interesting thing about this image is this white clast here. So there's a lot of diversity of rock types evident on the surface that everyone's excited about. So we might talk more about that. Whoops, I think I skipped. Yeah, here's I mentioned perched boulders. There are a couple of images where you see these boulders that on Earth would defy gravity. And there are 3 of them right here. And then maybe this one too. At least they look that way. But they're common on Bennu, and it's because the gravity is so low. But it leads to some very interesting terrains. And again, you see in this image the great diversity of what looks like a great diversity of rock types. So the cratered surface, the craters are not really well defined, and this was a first attempt by Walsh et al. Study earlier this year, trying to map out the craters, and you can see, the craters are very weakly defined, and there's a lot of interpretation involved here. Given that, they used the abundance of these large craters to suggest a relatively old surface age. I think I mentioned this already, between 100 million years and 1 billion years in age. So that's pretty old. I mentioned already, Bennu is an active asteroid. Apparently, there are these little particles that are being ejected. And I think the most likely hypothesis is that they're being fractured by temperature swings at the surface. And because there are water-bearing minerals in the rocks, the temperature swings might induce fracturing and particle generation. So I think this is a front runner idea, but there are other ideas being thrown around, I think, and so it's actively debated, in other words. So the next big event is the sampling, and I wanted to talk a little bit about that. So the site selection process is nearing the end. They need to so I'll show you in a minute the 50 sites that they initially identified. During the detailed survey, they wanted to narrow that down to 12 and then ultimately down select to 4. And then from those 4, select a primary site. So this is a complicated process. It involves components, decision-making components of the science value, sampleability. In other words, how is it even possible for that sampler head to get to the surface? Safety, is it safe? Is a spacecraft safe if you try to sample in an area? And then deliverability, which is just being able to back off the asteroid safely and stow the sample on board within the requirements. So these are all the components that go into that. The selection board is made of a variety of people, you can see here. And as I mentioned, they're right in the midst of that. And here's a map. So this is maybe the image that Andy mentioned earlier that he saw in Tucson. This is a global image of Bennu. There's a little aberration here at the edges as you get near the polar areas. But you can see all these purple circles are regions that they identified immediately as potential sampling sites. A lot of them are craters. Craters turn out to be the smoothest and most regular surfaces on Bennu. And here are a couple of examples. So this is a crater here. That's the width of this image is 65 meters. And this site has been one to be considered. If they were to sample here, you'd see they'd get a diversity of rock types here, the bright white ones and dark. So scientists were excited about this. And this one, on the other hand, here's the crater down here, but there are a number of obstacles that are nearby. So they need to get very accurate navigation between these boulders to get into that area, which is about 15 meters. So pretty small. Okay, so how does the sample collection work? So this is the spacecraft here on the left, and you see this TAGSAM arm coming down here. At the very tip of the arm is what we call the TAGSAM head, and that's shown up here, looking down on it from the top. And then on the right here, you can see it from the side in the high bay during the construction of the spacecraft. So this head has a wrist joint that gives it flexibility when it's touching the surface. And then it's got the elbow motion as well for flexibility. So when it touches down and actually touches the surface, there are jets of gas, nitrogen gas, that will push material. You can see these little arrows here, pushing material up through a flap in the bottom of the head and into this cavity right on the edge here. So the idea is that as the head touches the surface, you fire the gas pushes material up inside the head, and that all takes about 5 seconds as it's touching the asteroid, and then it slowly bounces off. And when Lockheed Martin has tested this in their various facilities, they can collect anywhere from 300 grams to almost 2 kilograms. And they've tested it in zero G in the zero G flight Here, KC1, yeah, thank you. Before the program changed. So they did a lot of testing back in 2010, 2011 timeframe. Anyway, once it's collected, then they stow it in the SRC here, and the lid closes, and it's safeguarded for the journey. Before the lid closes, though, they'll be able to image. They'll be doing some imaging from this little instrument down here, which is showing the imaging cone. And it'll be able to image the top of the TAGSAM head, the side from this point, and then the bottom. So they'll get that imaging. They'll learn from that maybe how much material they've collected, and then it will also do a series of inertial movements from which they'll be able to calculate the mass in the head compared to an empty head. So that'll give us a rough estimate, I think plus or minus 100 grams, how much material will be in this TAGSAM. Now they can go back. They have the ability to go back twice, 2 additional times, if they feel that they haven't collected enough material. So they can try again. But after that, that's it. So when it comes back, that 2-year journey back from Bennu ends with landing in Utah. So these are some images of the Stardust Return, which came back in Utah too in 2006, just to give you an idea of what we're hoping will happen. So there'll be a lot of training exercises in Utah getting ready for this. We'll build a portable clean room. This is the one that was built for Genesis, which also came back in 2004 in Utah. And so there'll be a clean room. That's where the sample will be taken. We'll have that ready, up and ready. This is the entry of the Stardust capsule. And up here at the top, that's what it looked like coming in. And when they found it out on the range, this is what it looked like. It had sort of rolled in a circle here, carved out a circle in the dust on the ground. Here's the recovery team. And then they put it, it comes down with a parachute. Yeah. That's an important fact I left out. Yeah. Yeah, it comes down to the parachute. So it's not a hard landing, but it's not exactly soft either. Yeah. And Stardust worked really well, and for that, given all that, and then they put a purge on it and put it in this box for transport to JSC. So material that'll be returned will be of 4 different types. There'll be the bulk sample, and this is a look into the TAGSAM head in some of the tests. And then on the bottom of the TAGSAM head, there'll be 24 of these little contact pads. This is a slightly less than an inch in diameter here. And these contact pads will pick up material too, we're hoping. Then there are some hardware items in the cover, the TAGSAM cover that we'll recover. And there are a bunch of witness plates that'll help us determine how much contamination, hopefully not much or none, the TAGSAM head has received from the spacecraft assembly and the environments that it witnessed. So we'll have a number of these little plates, these little circular sapphire and aluminum plates that we remove as well to archive. So the bulk sample, this is an indication of, again, how the sampling works. And you can see all that material gets pushed up into this these side, kind of a ring cavity, ring-shaped cavity that looks like this when you take it apart. And here's some test results that, as I mentioned, gets between 300 grams up to almost a kilogram in this particular series. So there's potentially a lot of material being returned. And as you get to finer grained material, it's easier to pack this head full, so that the 2 kilogram number that I gave you earlier, that's for really fine grained material. The coarser grained material like this results in maybe 500 grams, so slightly less. And then the contact pads. So here's a good view at the bottom of that TAGSAM head. There are 24 of these around the edge here, and they're little stainless steel Velcro hooks that look like this in if you look at the company's webpage, this is what they show as how they look beforehand. And then after, with tests with real materials, they look like this with particles trapped in there. And so we're currently testing ways of removing particles from these little Velcro hooks. And the witness plates I already mentioned, they're located not only on the TAGSAM head, but inside the cover here and here. So there's a lot of detailed work we've got to do with those. And finally, so the point of this slide is really that the Curation has been involved in this mission from the very beginning. And it really got serious in about 2014. Already 5 years ago, we started receiving materials for the archive, spacecraft materials. So we have a collection of about 500 items at JSC that are used for contamination knowledge with respect to the samples. So we've done a fair amount of work already, even before collecting samples. But we're going to be we are building a new clean room facility right now. And then we'll be participating in sample recovery. And then also Curation scientists will be involved in the examination of the samples and producing a catalog. And then the long-term curation as well. So it's a long process. I think I had to put together a 15-year budget for this mission at one point, which was a challenge. So here's just a quick look at the facility. This will be, if you know, Building 31, over at Johnson Space Center, the second floor, kind of the southwest corner or end of the building, will be totally transformed. What's now sort of a mixture of office space here will be transformed into 2 clean rooms, the OSIRIS-REx clean room, and then another one, the Hayabusa 2 clean room. So it turns out that NASA and JAXA signed an agreement to exchange samples from the 2 missions. So NASA will be giving 4% of, 4%? No, half a percent of our sample collected to Japan, and Japan will be giving 10% of their sample to NASA. Sounds like a mismatch, but because they collect such different amounts of material, it ends up being about the same. So it's a good deal for everyone, I think. So this just began construction. We're hoping it'll be complete by early next year. And the goal is to have the labs up and ready at least a year before samples are to be returned, so that we can get the facilities ready and be prepared rather than rushing around at the last minute. And so we'll be outfitting the labs to do that with a number of cabinets and storage boxes, processing cabinets, and putting different kinds of instrumentation in there as well. Some of it we'll have outside of the clean room that's already in our building. And we've been doing some preliminary testing, moving around small particles. So these are some really tiny 5 to 10 micron particles here, some larger ones up here, maybe 100, 250 micron size particles. This is the size range that we may have to work with, and we've never done really detailed work with individual particles like this. So it's important to get some experience with it beforehand. And I just wanted to end talking about and reiterating some of the science goals. So one of the main science goals is to look at the geologic history of Bennu, and that might include a pre-solar epoch. So there are, we have in some carbonaceous chondrites, we have little grains of material that survived from earlier than our solar system. So this is a crossover with astrophysics. The next epoch is the protoplanetary disk. This is really early, the first couple million years in the solar system. We're hoping that these samples provide some constraints on that epoch. Then there's a geological activity epoch, and this might be some of the more familiar geological processes that occurred after the origin, but before some of the dynamical processing and regolith evolution that may occur on the surface, or effects of from which may occur on the surface. And then finally, the current, what's happening currently. So we'll be looking at all these kinds of time frames, hoping for constraints. And then I wanted to just reiterate these outstanding questions. We're hoping that all of these samples will help us address some of these that I mentioned at the very beginning of my talk. You know, what forces drive the orbital change, and what's the internal structure? What about what are the organic compounds like on Bennu, and how do they compare to what we see in meteorites? And then can we make any connections between Bennu and specific meteorite types in our collections, or is it something we just simply don't have? And then finally, I know a lot of people are interested in how collecting how extreme the differences will be between having a pristine asteroid material and just regular meteorites in our collection. That'll be a really fundamentally interesting thing for all of us sample scientists. So that's what I've prepared, and I just wanted to end by saying that if you're an asteroid fan, you should keep your eyes and ears open for these two missions: the Psyche mission, which will be visiting metal-rich asteroid. It launches in 2021, and then the Lucy mission. These are their mission logos here. Lucy mission is visiting Trojan asteroids, and it's launching in 2022. So neither one of these are sample return, but they'll be really interesting anyway. And I also wanted to let you know about these resources you may find on the web and various other media if you're interested in more information. So thank you very much. I'll be happy to try to answer questions.
Great, thanks. Thank you, Kevin. All right, so we'll start here. On right there. Start off right there.
Hi, enjoyed the talk. Thank you. You mentioned craters and collisions quite a lot. I was wondering, do you have any thoughts about when other asteroids hit this asteroid? Is it going to dramatically affect the orbit of Bennu over its history? And also, if it's really a rubble pile, will that affect, will it absorb the impact more than, say, an elastic collision would have done?
Yeah, you know, that's not really my field of expertise, but I think that, this might be a little guesswork. But yeah, I think definitely rubble pile will behave differently than a rigid, single or a couple of pieces of more rigid body. And so that's where modeling comes in. I think, people have to be doing, and maybe some of this modeling's been done where you impact two rubble pile type bodies, or a rubble pile in a single or more rigid body, and see what happens to the fragments. But yeah, that's I think that's one part of your question. The other part is so the diversity of material that we see on the surface seems high. There are a lot of bright clasts and a lot of dark clasts, and even a lot of intermediate different shades. And so it suggests that maybe Bennu is a collection of unrelated materials. But one thing that'll be really interesting to look at is when they get close to a sampling site, the imaging will be at a more detailed level, and we may be able to see much more detail at the scale at which the samples will be collected. And so having that information together with all the detailed work that we do on the samples may allow really robust understanding of the connection between lithologies or the disconnect. There may be totally disconnected. So there are some meteorites. They're not all that common, but there are some, still significant numbers of meteorites that contain foreign clasts of material. So they might be 90% of a chondrite type, and then 10% is this other, like something like Vesta material mixed in. And so that may be possible on Bennu. It may be a carbonaceous breccia that has some clasts of a foreign, maybe an impactor or a piece of the body that got impacted multiple times and mixed in over time, over geological time. So it'll be, anyway, it's really, people who study breccias are really excited about this body so far because it may help to understand how they form.
Yes, you talked about the dynamic activity going on, ejecting particles, hygroscopic activity apparently. Now you grab the sample and you're bringing it back from the deep cold of space to Earth. I'm going to guess that there's volatiles and gases that are contributing to that process that are valuable to capture and understand. What processes do you have in place to know about the gases that are coming off of this?
Yeah, so the gas, that's tricky, and but there is a plan, and it's sort of a so it's not an ideal plan, but it's the best we can do, I think, given the technology and the time frame for launch and the level of technology and so forth, or the budget, the mission budget is also a big driver. But the way the volatiles will be studied is I'm not sure if I can. Let me go back and see if I can find let's see. We're getting close. Here, this little filter here, this is a two-way filter. So it's designed to keep air out. So when the SRC lands in Utah, there'll be a short period of time over which this filter can stop the desert air from coming in, or moisture, particulates, maybe about an hour, something like that. But it also has since it's a two-way filter, it can trap any gas or particulates that are given off by the sample, either during the return cruise or in this specific entry event. And so that material will be trapped on one side of the filter. That's the reason we'll be removing this and archiving it. We'll be taking that filter apart, and there's a team of scientists who will analyze the filter, trying to measure any volatile compounds that are trapped in there. So that's one way. The other way is when the spacecraft comes back and the SRC is still sealed with the sample inside, they'll be able to purge or push the gas that's trapped in there with the sample out. And we'll be there with sampling bottles to trap the gas as it comes out of these ports. And so that should also allow us to identify volatile compounds that may be in there. So as you can see, it's not ideal. And it's slightly less control than we'd like to have, but it should allow us to gather some information about anything that may be trapped.
As a follow-up question, does that change your thinking at all about how you're going to curate this stuff?
Oh, not really. I mean, there may be some things I haven't thought of yet, or we haven't thought of, that will be impactful, but so far, it's sort of what we expected. Material with a very high percentage of phyllosilicate material. That's what CM chondrites are made of, and that's what we were expecting, really. So we'll see. It'll be really interesting to see how much is in there.
Okay. Since we're still on ejection particles, when your slide was showing, are the ejection particles constantly being ejected? And if that is true, does that mean that Bennu is gradually decreasing in size?
You might think that, yeah, but so there are two parts to your question. One is that there are definite events. I think they've observed 3 or 4 events since they've been there, so they're not continuous. And what drives that periodic nature, I'm not sure is understood yet. But the other interesting thing that they've observed is most of the particles fall back onto Bennu. There are only a couple that have escaped, and these are tiny. They're pretty tiny, but they have observed a lot of them falling back and reaccreting onto the surface. So that may actually help us understand the nature of the surface too, knowing that material gets ejected frequently and falls back. It's kind of weird.
You pointed out that Bennu seems to have a lot less really fine material on its surface than did the asteroid sampled by Hayabusa. Is that difference understood at all?
Well, I would say not by me. Not by me. We could get somebody else who could probably talk for an hour about about that. But yeah, I don't know. I mean, personally, I would expect a carbonaceous asteroid to be more friable and to be a finer grained than some of these S and V types that we see. So the S Itakawa or Hayabusa asteroid is an S type, and it was relatively smooth. But those are harder materials. So maybe it means that the forces that are acting on, so Itakawa is a really strange a deformed potato shape, and that smooth material is in what may be a deformation joint, and it could be that internal deformation that's producing fine material over geologic time. Maybe that's an important process that you don't see on these spinning tops. Maybe the spinning tops may just distribute material across the surface and not really generate a lot of stress or force to break material up on that scale. I don't know. I'm sort of guessing, but that's a great question. Yeah, I think we'll hear a lot about that at these meetings.
Take one more here.
Kevin, I think there's one thing we have to keep in mind. Mother Nature throws us curves quite often, and I think you've already seen it on the surface of Bennu. But let me point out one to expect. 50 years ago, we had a carbonaceous chondrite land on the Earth, a CM carbonaceous chondrite, which we found an abundance of organic matter in, including amino acids. We kind of expected that to be the standard for CM chondrites. 2 months ago in Costa Rica, we had a very, quote, volatile-rich carbonaceous chondrite, a CM, when land and samples were picked up immediately after it fell. From what I have heard, the analysis of that does not match our standard for CM carbonaceous chondrites. There are no organics or amino acids, or minimal, that had been detected in this CM chondrite, which everybody thought was going to be juicy.
Yeah.
So keep your eyes open, and Mother Nature will keep us surprised.
Yeah. Thanks.